Hi, this is Mrs. LaBarbara. This is Physics Chapter 6, Momentum and its Conservation Video 4. Today's topic is types of collisions. The objectives are know the definition of inelastic collision, elastic collision, and explosion. Be able to apply conservation momentum to different types of collisions. Types of collisions: elastic, inelastic, and explosion. Elastic collision happens if two objects bounces off each other when they collide. The first animation, this is an example of elastic collision. The car and truck bounce off each other. Inelastic collision is the collision if the two colliding objects stick together and move with the same post-collision speed. Take a look at this. Car and truck collide and stick together, move with the same speed. Explosion is the collision happens when the system is at rest initially. Then it separates into different parts. In this case, the two cars are at rest. Maybe there's a spring in here between them. When the spring is released, one car goes backward, one car goes forward. So this is called explosion. Explosion is a system at rest that separates into different parts. The total momentum equals to 0 after collision. So in all the collisions, momentum is conserved. Let's talk about inelastic collision. Again, inelastic collision happens when two objects stick together, have the same speed after collision. Here is an animation for inelastic collision. So this car, one flat car is at rest. Then diesel comes, hook up to a flat car, so both are traveling. So let's take a look. In all collisions, momentum is conserved. P before equals to P after. P before is total momentum before the collision, m1 times v1 plus m2 times v2. That's the momentum of the first object plus momentum of the second object before collision equals to momentum of the first object after collision plus momentum of second object after collision. Since after collision, both objects have the same speed, so v1 prime equals to v2 prime equals to v prime. So we can rewrite this equation equals to m1 v prime plus m2 v prime. We can factor in v prime out. So this is the equation we have. This is really not another equation. It is a derived equation for conservation of momentum. For special case, the special case is inelastic collision. Now we're going to use this equation to solve some problems. First example, car A, 50 kilograms, approaches to car B, which is at rest, with the initial speed of 30 meters per second. So this car A is moving at 30 meters per second. After the collision, two cars lock together. This is a case of inelastic collision. Question is, with what velocity do the both cars travel? So what is the velocity they travel? Okay. So let's see, write down MA is 50 and B is 100, VA is 30. That's VA is 30, VB is at rest, so VB equals to 0. After collision, the two cars, what is the speed of the two cars? So let's use conservation momentum. This is momentum before MAVA plus MBVB equals to momentum after. Since two cars lock together, this is inelastic collision. We combine the mass of the two cars times V prime. So all you have to do is plug your numbers in, make sure 50 is the one has 30 meters per second. 100 kilogram car was at rest. So make sure you put the mass and velocity in the right place. And after the two add together times V prime. So V prime in this case equals to 10 meters per second. So as you can see, before it was 30 meters per second, but when it locks the second car, together they will travel slower. That is because the total mass that moves have changed. Mass before was only 50. Now mass after the total mass is moving is 150. So mass doubled, mass tripled, therefore speed has to decrease by 3 times because total momentum is conserved. Another example, pay attention to direction. Again, momentum is a vector quantity, so direction is very important. Car A is moving with the initial velocity of 30, approaches to car B, which is moving at 20 meters per second toward car A. So if car A is moving with positive, then car B has to move with negative because they are in the opposite direction. Again, two cars lock together and moves as one. What is the magnitude and direction of the final velocity? So let's write down what you know. MA is 50 and B is 100 kilograms. VA car A is moving at positive 30 meters per second, but car B is moving at a negative 20 meters per second. So here's after the two cars has the same velocity, VA prime equals VB prime equals V prime. What is that equals to? Conservation momentum, momentum before equals to momentum after. Plug in your number. So V prime is 3.3 meters per second to the left. This is because car B has more momentum than car A. So therefore, when you add these two together, the net momentum is to the left. Sometimes in physics, we have to use symbols instead of numbers. So you need to get used to the idea of using symbols to solve problems. A block of mass big M initially is at rest on a frictionless horizontal surface. You see this frictionless, that's indicate momentum is conserved. This is an isolated system. Is struck by a bullet of mass little m with horizontal velocity v. Now when the bullet will be embedded in the block, what is the velocity of the bullet block system after the bullet embedded itself in the block? So here is before the collision, this is after the collision. What is the momentum before the collision? M times V plus big M times 0 because this big block is at rest. Momentum after collision is these two mass together move with the same velocity V prime. Obviously, the two are the same. P before equals to after, that's the law of conservation momentum. So we simply solve for V prime. To solve for V prime, you have to divide this term by both sides, the term of M plus big M. So answer is MV divided by big M plus little m, that equals to V prime. Another example. A woman with horizontal velocity v1 jumps off a dock onto a stationary boat. After landing in the boat, the woman and the boat moves with velocity v2. Compared to the velocity v1, velocity v2 has same magnitude, same direction, same magnitude, opposite direction, smaller magnitude, same direction, larger magnitude in the same direction. So some of you probably instinctively know the answer should be 3. The answer is 3. So for those of you who cannot imagine why the answer could be 3, here is an animation for you. Imagine this blue, that's the woman. Okay, is running. Jump to this boat, is at rest. As you can see afterwards, they are traveling slower than before the boat. Well, total mass has to move increased. So the velocity has to decrease in order for the momentum to be conserved. So the answer is 3. Another type of special case of momentum conservation is explosion. So explosion happens when initially the momentum is 0. Then, for example, this tennis ball in a homemade cannon. When tennis ball is fired, the cannon is going to go backwards, but the total momentum is conserved. So total momentum after equals total momentum before. Total momentum before is 0, so total momentum after has to be 0. Total momentum after is the momentum of the cannon plus momentum of the ball. So they have to be opposite and equals to each other. If the ball has momentum of 5, positive 5, then cannon has to have a negative 5. If the ball has positive 50, then cannon has to be negative 50, because total momentum of the cannon and the cannonball, the tennis ball, added together has to be 0, because total before is 0. So here is conservation momentum, P before equals to P after. P before is 0, so after has to be 0. We can use this equation to solve for one of the velocities. If we know one velocity, we can solve for the other velocity. Here is an example. A 2-kilogram rifle initially at rest fires .02 kilogram bullet. As the bullet leaves the rifle with a velocity of 500 meters per second, what is the momentum of the rifle bullet system? So right away, some people probably have a tendency trying to calculate. You multiply, divide, and trying to find all different numbers. But for those of you who are pay attention to the concept, what is the rifle bullet system? What's the momentum of rifle bullet system before it was at rest? So before, the whole system has 0. So after has to be 0. So total momentum has to be 0. The momentum of the rifle bullet system is 0. So really, this is concept question. There is no calculations. Let's take a look at another example. A 60-kilogram man standing on a stationary 40-kilogram boat throws a .2 kilogram baseball with a velocity of 50 meters per second. With what speed does the boat move back after the man throws the ball? So the important first step here is to figure out what is the system consist of. The system actually consists of a man and a boat, that's one object, and a ball, that's another object. So before, they are all stationary. So total momentum before is 0. After, when the man throws the ball moves in one direction, but the man and the boat has to move in the other direction in order for the total momentum to be conserved. So after is the man and the boat, the mass of a man and boat times V1 prime, plus M2, the mass of the ball, times V2 prime. The two has to be equals to each other. So the total after has to be 0. Simply substitute a number. The man and the boat is 60 plus 40 kilograms times V1 prime equals to both mass times both velocity. So you solve for V1 prime, that's the man and the boat, equals negative 0.1. That means you're going backward at much slower speed than the ball, because the ball's mass is so small, it moves a lot faster. So the man and the boat's mass is bigger, so it moves much slower. That's it for today. Thanks for watching. See you next time.